My name is Chris Harris and I'm from AlleryTutors.com, and welcome to this video. This is a revision video for AQA. In particular, we're going to look at the introduction to organic chemistry. So basically, we're just going to go through an overview of this topic that's just designed for revision, really, to give you a brief insight into the topic to make sure that you've covered most of the things. The PowerPoints that I'm using here, you can purchase them. You can get them from the link in the description box below the video. If you click on that link, it will take you to the place where you can buy them from. Like I say, this is very specific to AQA. So we have the points here. This is what it says in the specification. So it's just making sure that you're able to obviously address these points so you can answer the questions in the exam. Okay, so let's have a look first. We're going to look at the types of formula. There's a few of these. You need to know these formulas, and it's all about application in the exam of these. So the general formula is basically an algebraic formula that can be applied to chemicals in the family. So for example, alkanes, alkenes, alcohols, etc. So you can see here that we've got some examples of general formulas here. So we have an alkane, which is CnH2n plus 2, and we've got alkenes, which are CnH2n. Obviously, we have the lack of the two hydrogens there. And then alcohols are CnH2n plus 1 OH. So as long as you can state these general formula, they're pretty important. Okay, so you've got to be able to, you've got to know how to do that. Okay, right, so molecular formula. So these are the actual number of atoms in a molecule or element. So the molecular formula is basically just something like C2H6. So this is ethane, for example. So these are the standard formula that you may see when you write out your chemical equations. Empirical formula. This is very similar to the molecular formula, except this is the simplest whole number ratio of atoms in a compound. Now these look a little bit odd because they don't kind of fit. So for example, if we use the ethane example we used before, that was C2H6. Its empirical formula is CH3. Now you look at that and think, well, that doesn't really look right because obviously carbon needs 4 bonds. But remember, this is just the simplest whole number ratio of a compound. So that's pretty important. Okay, structural formula. So this is the arrangement of atoms in a molecule without showing any of the bonds. Okay, so there's no bonds being shown here. So for example, if we use butan-1-ol, basically we're fragmenting or breaking the molecule down into CH3, CH2 chunks. So a butan-1-ol is CH3, CH2, CH2, CH2OH. Notice there's no lines here to display the bonds. Just literally straight up, there's your formula. Skeletal formula. Right, skeletal formula, they show the bonds of the carbon skeleton only. Hydrogen and carbon atoms are not shown, but the functional groups are. So these are a bit strange. So here's an example. This one's butan-1-ol. Basically, each one of these points here is a carbon with hydrogens attached to it. So this is CH3, CH2, CH2, CH2OH. So we've got 1, 2, 3, 4 carbons with an OH on the end. We use these in chemistry because sometimes the organic, especially in organic chemistry, because, we do in organic chemistry because it can take a while to basically draw out your carbons and hydrogens, etc. It's just a lot quicker displaying it like a skeletal formula. It looks like a load of zigzags, but actually each point here is a carbon with obviously the maximum number of hydrogens that can fit around it. Obviously according to where it is in the molecule. So that's the skeletal formula. And your displayed formula, basically it shows the arrangements of all the atoms shows the arrangement of atoms, showing all the bonds and the atoms in the molecule. So for example, this is 2-chloropropane, and you can see here that we've got obviously all our carbons. There's the chlorine, look, sitting on the second carbon. But notice all the bonds are being displayed. They're all being shown, and all the atoms are. So we're not doing CH3, CH, Cl, CH3. We're literally showing everything. So it's all broken down. Okay, that's called the displayed formula. Make sure you're aware of that because they will ask for these specific things. Okay, let's have a look at a homologous series. So the homologous series of a group of compounds, they basically have the same functional group and they have the same general formula as well. So we need to know, obviously, we need to be able to apply these and work them out. So, for example, we're going to use the general formula to work out the molecular formula of a compound. So, for example, alkenes have this general formula, CnH2n. N is the number of carbon atoms. And the molecular formula of an alkene with 23 carbons is basically this. So we've got C23H2 times 23, because we've got, obviously, H2n. So N is just the number of carbons, so that's going to be 23. So this is going to be C23H46. So this is the general formula, and we're using this to work out the molecular formula that we'd seen before. Now, successive members of the same homologous series increases by CH2. So, for example, the general formula for alcohols is CnH2n plus 1OH. So you can see here we've got methanol. Ethanol, look, is in the same homologous series, just adding an extra CH2. Propanol, add an extra CH2. Butanol, add an extra CH2. So these are successive members of the same homologous series. So we need to know, obviously, the specific types of homologous series. So alkanes, they all end in ane. And, for example, butane, there's an example there. Alkanes, which are branched, they have an alkyl group. So, for example, it would be methyl propane. So this is basically a methyl group on the middle carbon there. So this is methyl propane, so we just say alkyl. Alkenes have the ending ene, E-N-E. Okay, the example is propene, CH3, CH, CH2. So basically just end it in ene, so it's pretty straightforward. Alcohols, they end in OL, so this is like an alcohol, ethanol, look, there it is, CH3, CH2, OH, ethanol, alcohols. Aldehydes end in al, so that propanal, for example, there's an aldehyde, so CHO at the end. Ketones end in one, so O-N-E, so that's propanone, for example, so CH3, CO, CH3. Carboxylic acids, they end in oic acid. So, for example, butanoic acid. So, CH3, CH2, CH2, COOH, the end in this bit here, COOH, COOH. So, look out for that. That's a classic sign of a carboxylic acid. Halogenoalkanes. So, these are things like, you'll come across these. Fluoro, chloro, bromo, iodo. So, for example, bromoethane is this one here, CH3, CH2, Br. And the final one is cycloalkanes. So basically you just put the word cyclo in front of it and end it in ane. So for example, cyclopentane, C5H10. So make sure you know these functional groups. They're really important. Obviously naming them is going to be crucial. You are going to be expected to name these molecules. So make sure you do know them. Okay, so talking about naming, let's actually look at some. So this is nomenclature, which is the posh word for naming molecules. And we use the IUPAC rules. So IUPAC is basically like a governing body, a bit like FIFA for football. So basically this is like FIFA for chemistry, effectively. So these basically govern the rules and naming molecules and naming the elements of the periodic table. And it's got a very catchy name. IUPAC, it actually stands for the International Union of Pure and Applied Chemistry. Yep, you can see why they've called it IUPAC instead. Basically, this is the global language of chemistry, and they set these rules out, and they're really handy because it allows us to name long molecules. So the first thing we have to do is we name or find the length of the stem by counting the longest continuous chain of carbons. So the stem name, if it's got one carbon, it's meth. If it's two, it's eth. If it's three, it's prop. 4 is but, 5 is pent, and 6 is hex. And you can go on and on. You can keep on going. And you get 7s, 8s, 9s, etc. So basically you need to know the stem names. So we start with the stem name. So we find the longest continuous chain. In this molecule, the longest continuous chain is that one there. Okay, so that's 4 carbons. Really, really important. It doesn't matter. Even if it looks like a branch, it looks as though it's coming off another carbon, you just need to find the longest continuous chain in your molecule. I can't emphasize that enough. If you don't find that, your molecule will not be named right. Okay. So, functional groups on the molecule normally tells you the ending of the name. We call that the suffix. So, basically, it also has an OH group, this molecule here, which means that this one will end in ol, because we've got two OH groups in this one. Okay, so the third thing, what you have to do is number the carbon chain. So the functional group sits on the lowest possible carbon number. Now, I can name this in two ways. I can either name it 1, 2, 3, 4, or I can do it this way, as this is suggesting, 1, 2, 3, 4. And because I've named it this way, because my functional groups sit on the lowest number, if I numbered it from here, 1, 2, 3, 4, these OHs would sit on the fourth carbon. Now, 1 is obviously lower than 4, so we name it from, or we number it from this way round. And then what you have to do is make a note of the carbon number to the OH is attached to, and place this number before the suffix, and this is a type of butan-1-ol, this one here. So again, we're going to put obviously 1 because it's sitting on the first carbon, and we put that before the suffix at the end. Okay, so any side chains and less important functional groups are written as prefixes in alphabetical order. Okay, so this is really important. So in this case, we obviously have a methyl group. There it is there. We've got a methyl group hanging off this third carbon, carbon number 3. And finally, if there is more, or if there are more, should I say, more than one identical functional group or side chain, we put di, tri, or tetra in front of it. So di for 2, tri for 3, tetra for 4. So this one here is 3-methyl-butan-1,1-diol. Okay, right. So let's just break this down a little bit. We've got 3-methyl. We've got a methyl group there sitting on the third carbon, carbon number 3. Butan, because we've got longest carbon chain, is butan. And 1,1, because we've got 2 alcohol groups sitting on the carbon number 1. So we call it 1,1. And di, that tells us we've got 2 of them, ol, because obviously it's an alcohol. So make sure you be able to name that and look for the longest carbon chain. Okay, mechanisms. Right, so a chemical mechanism shows the movement of electrons during a chemical reaction. Now, organic chemistry is all about mechanisms. You have to be able to show them to show how reactions occur. And the arrows are crucial, so you need to know about these arrows. So we use a curly arrow to show the movement of a pair of electrons, and you'll see this throughout the rest of the organic chemistry topic. They always start from an area where there's lots of electrons. That could be a double bond or lone pair. And you can see we've drawn the red arrow there. Basically, the end of the arrow is basically showing you where the electrons are moving to. Or it could be the formation of a new bond. And sometimes it is. So, free radical mechanisms. We don't require any curly arrows. You'll see free radicals in the halogenols topic, halogenoalkanes topic, but we don't need to know them for this. So that makes it a little bit easier. A mechanism showing how an OH minus reaction reacts with bromoethane. Okay, so let's have a look at this as an example. So you can see here that we've got an OH minus and a bromoethane molecule. Basically, we've got the lone pair. Now, curly arrows basically show this bit here. Look, the electrons are moving from a lone pair to a bond, or they're trying to form a bond with the carbon. So if you look, it's going from an area where there's loads of electrons to a delta positive carbon. Okay. Also, this one's forming a bond here, but also the curly arrows can show how we can break a bond as well. Electrons are in this bond, but the electrons are now moving onto the bromine here. So the arrows are representing the same thing, but they always start from an area with electrons, either a lone pair or a bond. This is showing bond making, this is showing bond breaking. So it doesn't really matter, curly arrows can be used to demonstrate both. Okay, and obviously the final product in this case, is just the example, is we form an alcohol here, so this is ethanol, and a bromide ion as well. So yeah, and we did have sodium in here because we're going to react with sodium, if it was sodium hydroxide, but it's a spectator ion, it doesn't actually get involved with the reaction. Okay, so make sure you know mechanisms. You'll see them quite a bit anyway in the organic topic later on, which is just showing you kind of an introduction to it. Okay, structural isomers, so chain isomerism. Right, you need to know about all these different types of isomers. So structural isomers have the same molecular formula, but a different structural formula. Okay, so there's 3 types here that we need to know, is chain, positional, and functional group. Okay, and we're going to go through each one and make sure we know what they are. So we'll start with chain first. So basically, definitions are important here. Same molecular formula, but different arrangement of the carbon skeleton. Okay, so let's have a look at an example. So here's pentane. And an isomer of pentane could be 2-methylbutane. Now, both of these formulas have the same molecular formula, but the arrangement of the atoms, as you can see, is different. So this one has just been shuffled around a little bit. But if you count the number of carbons and hydrogens, they'll be the same as what's in pentane. So these are actually isomers of each other, chain isomers. Okay, right. So let's have a look at positional isomers. So these have the same molecular formula, so same as before, but different position of the functional group, okay, of the carbon skeleton. So positional, look at the word before the word isomer. Positional is the change of position of the functional group. So here's an example. This is pentan 1-ol, and the positional isomer of pentan 1-ol is pentan 2-ol. So the position of the alcohol group has moved. It's moved from the end to the middle. And that's a classic sign of a positional isomer. And functional group isomerism, this is basically, again, the same molecular formula, start with the same thing, but a different functional group. The word in front of the isomer tells you what's changing, so it's the functional group that's changing. So, for example, here's pent-1-ene. Basically, we need to have a molecule that doesn't have an alkene in, but has the same molecular formula, and that could be something like cyclopentane. So cyclopentane has the same molecular formula as pent-1-ene. So you count the number of carbons and hydrogens, and you'll see that from there. But you can see, crucially, there's no double bond. So it's definitely a functional group isomer. Okay, you also get these types of isomers as well, which are stereoisomers, or also known as EZ isomerism. Now these are a little bit tricky. So stereoisomers have the same structural formula, okay, but a different arrangement of atoms in space. Okay, so an example is an EZ isomer, okay, that you need to know. You also get optical as well, but optical isn't covered at AS, so you're fine with that. But you've got stereoisomerism. So we've got a CC double bond, okay? All these things do when you're looking at EZ. Okay, so we're looking for the alkenes. And the atoms are bonded directly to this are flat, they're planar, okay? So the atoms can't rotate around this bond because it's rigid, it can't move. And this means you get some special type of isomerism, which we call it stereoisomerism, or EZ. So let's have a look at these two examples here. So these are two stereoisomers of each other. So they have the same structural formula, CH3, CH2, CH, CH, CH3, but we can't twist the double bond in order to turn one isomer into the other. So if you look at this one, there's the double bonds. This can't rotate. So you can see this one and this one. You can see the main difference is basically the CH3 on this one is down here, whereas this one, it's up there. So because this can't twist, I can't flip that one round to match this molecule here because that's fixed. And because I can't do that, this molecule is different to this one. And that's what we call an EZ isomer. So let's have a look. So we've got these two isomers have restricted rotation around the double bond. Okay, so we get EZ isomerism when you have two different atoms or groups of atoms on the same carbon. So if we look at these two here, there it is. Look, two different ones. We've got this one and that one. These two are clearly different, and these two are different to each other. So that's where we get EZ isomerism. If we had two hydrogens on the same side here, hydrogen there, we wouldn't get EZ isomerism. Okay, so we're looking for two different groups. So we can name these molecules as E or Z, and E stands for entgegen, which means opposite. And these are the same groups that are opposite the double bonds, and we can label them as Z or zusammen, which means together. And these basically the same groups are on the same side of the double bond. So let's label these ones. So this one is Z pent-2-ene, because look, the molecules or the hydrogens, or you could use these ones, but the hydrogens are on the same side of the double bond. Look, they're both at the bottom, so we call that Z pent-2-ene. But look at the hydrogens here. The hydrogens are now opposite the double bond, so we call this one E pent-2-ene. And it's pretty much as simple as that. Now it gets a little bit trickier when we have, let's say we have groups which aren't the same. So in the previous example we had the two hydrogens obviously. What happens if we don't have two hydrogens? Well then what we have to use is something called the Cahn-Ingold-Prelog rules, or also known as KIP rules. Now, you've got to be really careful with these, okay? So we use these Cahn-Ingold-Prelog rules, or CIP rules, KIP rules, when deciding if an isomer is E or Z when we have four different groups around the double bond. So look at this example here. You can see that we've got four different groups. Unlike the previous one, we had two hydrogens. Here, Now what we've got is a H, a Br, a CH3, and a CH2, CH3 attached on here. So all these are different. So that's going to be really difficult when we're using the normal rules. So what we do is we label the carbons with a double bond as carbon 1 and carbon 2. And you can see that we've labelled them there. Then what we do is we calculate the atomic number of the first element directly bonded to the CC bond. This atom, so the atom with the highest atomic number is given the higher priority. Now remember, it's atomic number, not mass number. Okay, so it's the number of protons, the proton number, or the atomic number. So don't get them mixed up. Okay, so looking at these two, obviously CH3 has an atomic number of 6, or the carbon, sorry, has an atomic number of 6 because you're looking at the first element, and bromine has an atomic number of 35. Bromine's got a bigger atomic number, so it's given the higher priority. So let's look at the other side. So again, carbon on the left there has the higher priority. It's got 6, and the hydrogen on the bottom there, this one here, hydrogen has a lower priority. It's got an atomic number of 1. So the two higher priorities are actually opposite the double bond. So this is what we're saying here. So the two high priority groups are on carbon 1 and carbon 2 are opposite sides of the double bond. You can see they're opposite the double bond. There they are. So in that case, we call this one E. 2 bromo pent 2 ene. The E bit tells us that it's opposite the double bond. Okay, so it's pretty straightforward there. Okay, so these are your, make sure you can obviously assign these and you can use these. It's pretty straightforward. Just remember that this is the proton number, not the mass number. Okay, so you may have to check further down the chain though to work out the priorities. So let's have a look. So here on carbon 2, there are 2 carbons immediately bonded to it. You can see here, there they go. So these would have the same priority normally. So both have an atomic number of 6. But if we look at the next atom down the chain, there's another carbon on the ethyl group. So it's here, there's the other carbon. This has an atomic number of 6, but just a hydrogen on the methyl group on here, which is an atomic number of 1. So basically, obviously if we look at these ones, this has got the higher priority on this side. But look at this one, the atomic number is 6, then 6, because we've got 2 carbons. This one is 6, then 1. So because this goes to 1, this is a lower priority, and this one's a higher priority. So just keep looking down the chain and just add the numbers up. So the ethyl group takes priority, this one here, over the methyl group. And so again, we've got 2 higher priority groups opposite the double bond. So this one becomes an E. 1 bromo, 2 methyl, bute, 1 ene. Okay, so again, look down the carbon chain, make sure you know how to do that. And just a kind of trick, you've got to watch out for these isomers and make sure that you have actually drawn an isomer that's different. Sometimes they can get you to draw these isomers and you haven't just drawn one with a different shape. So basically you need to find the longest continuous chain. Remember I said that right at the start. Doesn't matter if the shape's irrelevant. We're just looking at the longest carbon chain. So let's have a look at this one. There's pentane. This one is still pentane. It looks a little bit different, but it is still pentane, believe me. So again, looking for the longest carbon chain. Look at this one, Z-butene. This one is still Z-butene. Okay, there is no difference. Even though the hydrogens are at the top on this one and they're on the bottom here, it is still Z-butene. So don't be tempted to draw this and call it something else. Okay, so make sure you're looking out for them. And that's it. That is your kind of quick introduction to organic chemistry. It just gives you an overview of the intro to organic chemistry topic for AQA. Again, if you would like to purchase this PowerPoint, you can. You can use it for whatever you want to do. If you just click on the link on the description box for the video underneath, you'll be able to get it there. But that's it. Bye bye.